Welcome to Module 2 of Hydraulics. In Module 2, we'll be studying about Pascal's law as it applies to fluids. And his law states, as you can see right here, first of all, these are kind of my interpretations of what I think of when I think of pressure. I think of strength. When I think of the rate of flow, how fast the liquid or fluid is moving. When I think of a valve position, I think of the direction in which I want the fluid to move in. And Pascal's law states pressure applied to a confined liquid is transmitted undiminished. That means it doesn't lose any pressure in all directions and acts with equal force on all areas at right angles. It applies to all fluids, and the two fluids that we talk about mostly are liquid, hydraulics, and gases, that would be air or pneumatic. Liquids are incompressible. They're stable. You can hold something up as long as it has flow. And if it's in a confined space, you can set something on top of a piston, let's say, that's sitting on top of hydraulic fluid, and it will stay there with whatever pressure you put on it without moving for ever how long you want it to be there. We will get to force multiplication, and we will talk about how we can take over here a small cylinder, apply 200 pounds, and then come out, as I have here, with 400 pounds because of this little formula I've got here. Pressure is equal to the force divided by the area. Over here, this 200 pounds would be a force. The area in this case is I made these numbers up. This is a 2-inch square. This is 2 square inches. This piston, that's the area, and it's a circle, as you can see, and we'll get into that kind of stuff later. So I'm applying 200 pounds of pressure to a piston down here, down in here. Whoa, all down in here is fluid, and it goes all the way over. And when I apply that pressure, that 200 pounds, or that the force is 200 pounds. The pressure I'm applying is 100 pounds. So that is 100 pounds here, all throughout this system. So the force is the weight, let's say, or how many pounds I'm applying to the fluid. And the force out will be determined by the same pressure, 100 pounds, going up against a much larger diameter piston. In this case, the area of this piston is 4 square inches. So this has got a factor of force out divided by force in is 2 to 1. So it can, it's, I think they call it a multiplying factor, would be 2 to 1s, or twice as much in this case, in this system. I could increase the size of this, I could decrease the size of this, or manipulate these to come up with the things I would like to have, the pressures I would like to have where I need them. This would be something like what's happening in the beginning, the in flow. And this is like what's happening out there at the cylinder on the excavating arm, or whatever the actuator is. The, the force multiplication trades distance for force. Okay, look over here. I'm moving this down 6 inches. And it's going to push this fluid, which won't change volume, up a little bit. But in this case, you look at this distance, you look at this multiplication factor, force multiplier factor, and you can see that it's a 2. So it's twice as much as this. So the distance traveled here is going to be half the distance that you had to move this to get this piston to at the actuator to move 3 inches. You had to move this, even though it's small, you had to move it 6 inches. And here's where this is not free. These calculations down here are me fiddling around, but this was just coming up with the 400 pounds that the force out 400 pounds, the force in was 200 pounds. So that's where the 2 to 1 multiplier comes in. But do you see that we had to sacrifice the movement of the actuator arm? We lost some distance. We gained a lot of force, twice the force as we put in, but we lost distance. And when you look at the overall scenario of what we've done not near as much work as, although this is going to come out, the law of conservation will apply here, and I'm not going to get into that. It's not a very complicated, but energy just is going to stay with us, but we're going to lose distance. So we may not be able to do what we want to do, and we may have to come back over here, increase the size of this or this to gain a little distance, to increase the factor. Now, I was doing some calculations, and I decided I don't want to really talk about them that much because we'll get to it later. But I was taking the volume, this volume, this 6 inches, you could figure as the height, like when you say what is the formula to find the volume of a cylinder? Well, it's a cylinder, so you got to find the area first, and I'm saying it's 2 square inches. And to find volume, you take area and multiply it times height, or distance in this case. And that would give you volume. Well, you can do all of those things. You can find distance by using that formula, but it's a bit complicated, and it includes a lot of transposition of variables. And I really don't want to do that right now. There's some shortcuts that we'll come into so that we don't have to deal with this, what I was doing down here with these transpositions, though we will probably talk about them. So let me see if I can shift. I'm not going to spend any more time on this. I just wanted this in your brain while you're reading through this, because it's going to talk about force multiplication, but it's not going to tell you much. It's going to tell you it has a takeaway. You have a price to pay. And that's what I was trying to illustrate, is although we used 200 pounds to lift 400 pounds, there was a price to pay. We could only move the actuator 3 inches and it took us 6 inches of motion here to get that done. So let me see if I can get over here to this other screen, and I may or may not get lucky with it. No. There. So you see I'm here. Maybe you can see my little hand. That's week 2. It's Pascal's law and force multiplication. I just want to go over the objectives and maybe say a few words. And right here's where I'm going to put this video so you can look at it as a reminder once the course starts. So our objectives are pretty well defined, and they'll cover the actual sections in the first part of the chapter that we will use that we will cover in week 2. So we're going to demonstrate an understanding of Pascal's law and its applications in hydraulic systems. So now you have a bit, not much, but a bit of a head start with that. We're going to demonstrate, we're going to know or understand Bernoulli's principle and its application in the hydraulic system. What Bernoulli says is that whenever in a system, in a hydraulic system, a fluid system, when you increase the flow, you will decrease the pressure. When you increase the pressure, you will decrease the flow, the rate of flow. And those two things that I showed you a while ago that I had. Pressure is strength, the power. Flow is the movement of the fluid through the conduit or whatever. But what this does and what it says is like, for instance, on a pump. When you start, and pumps, by the way, don't produce pressure. They produce flow. So you start a pump up and you kind of have a vacuum almost on the inlet side of the pump. And as it goes through that pump, the flow meets resistance, and that's what builds pressure. Resistance was a piston in our case. So it comes into play there. Now think about a garden hose, and there's a pretty in-depth explanation in the rest of this module 2 about Bernoulli's law. But you put your thumb over part of a garden hose, and what happens? Well, you decrease the flow, but you increase the pressure. You know how it streams out. Take it now. Let's take this into aviation, for instance. You know, how does a plane fly? And we can go about these guys watching birds and the way the wings are structured. But you look, as air flows over the top of the wing, it reduces its rate of flow. That increases pressure, according to Bernoulli. When you reduce the flow, and it does going over the top of the wing, but under the wing is the pressure increases, and there's more pressure under the wing than there is above the wing. So that's what keeps the airplane in the air. So Bernoulli's principle applies in a lot of cases, like what happens to fluid when it goes through the restrictions of a valve. And we will look at those things, but there's some pretty complicated calculations in determining what sizes and things like that. But we will be talking a lot about that. The terms used in hydraulics, I want you to take a good look at those. And it's not that I need you to memorize them, but I want you to understand them, what they mean, because you're going to come across things like hydrostatic. And we need to know what that is, you know. Discuss the advantages and disadvantages of hydraulic systems. Hydraulic systems are just, they have changed the world. You may have, the construction industry, earth moving for sure, but lots of other things too. Airplanes have all of their controls, hydraulic and things like that. But let me stop here. We have a lot to do in this course, and hopefully it'll be. I want it to be challenging. There's a little bit of formula stuff here. I think you may have. I don't think you're going to see anything that you haven't seen in your math class, because I think you were taught some things about manipulating formula. But if not, we'll do it here. We'll fit it in so that we all stay on the same page. And if something, and if you don't understand, give me a call. Just say, I have no idea. You know what 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 you were talking about. That's okay. I'd rather you be a little bit more definitive, but that's okay. Anyway, I'll be seeing you guys, or visiting with you guys at least. Let's see, what is it? Tuesday is this coming Tuesday is the first day of class, and we will start with Module 1. And I also have you in erosion control, and I think we have a video already up on that. So we'll see you then, guys. Thanks.